Hello, everyone, and welcome to today's live webinar, Structural Stability, Letting Fundamentals Guide Your Judgment, presented by Dr. Ronald Zenian. Today is April 16th, 2020. My name is Nate Goner with AISC, and I'll be your moderator for today's presentation. I would like to introduce our speaker, Dr. Ronald Zenian. Dr. Zenian is a professor at Bucknell University. He received his Bachelor of Science in Civil Engineering, his Master's of Engineering, and his PhD degrees from Cornell University. He is co-author of the textbook Matrix Structural Analysis, the developer of the educational analysis software MassDAM2, and the editor for the 6th edition of the Guide to Stability Design Criteria for Metal Structures. Dr. Zenian is very active at AISC. He is a member of AISC's Committee on Specifications. He's the chair of TC3 on Loads Analysis and Stability, and he previously chaired AISC's task group on inelastic analysis and design. Dr. Zenian also serves on the AISI and Aluminum Association Specification Committees, and he's active with the Steel Joist Institute, and he is the former chair of the Structural Stability Research Council. Dr. Zenian has been awarded the ASCE Norman Medal, the AISC Special Achievement Award, and the ASCE Shortridge Hardesty Award for his contributions to the profession related to stability analysis and design of metal structures. In 2019, Dr. Zenian was selected by AISC as the recipient of the T.R. Higgins Lectureship Award. And this today is his T.R. Higgins Lecture. Ron, thank you very much for being here today, and I will now turn it over to you.
Well, thanks, Nate. It's certainly great to be here and have the opportunity to present my lecture in the form of a webinar. Well, good afternoon, ladies and gentlemen, and welcome to Structural Stability, Letting the Fundamentals Guide Your Judgment. As Nate had indicated, this is part of the T.R. Higgins Award that I received, and I just wanted to give a little bit of background to Ted Higgins, or about Ted Higgins. He was the Director of Engineering and Research from 1945 to 1968 at AISC. And in the early 60s, so it would have been late 50s, right into the 60s, Ted was instrumental in putting forward the 6th edition to AISC's specification. And there were some very big changes that occurred with this specification. They included the effective lens concept. Prior to that, we were just designing for the unbraced length. Along with the effective length concept came moment amplification factors. And then new to the entire design profession was the opportunity to use plastic design. This specification included many other features, semi-tension field theory and the like. It really was a groundbreaking specification, one of the big three. Certainly this 6th edition, the first addition to the LRFD specification in 1986, and in 2005 when AISC came out with the combined edition. Those were all three big pieces. I do feel in some way I know Ted. I never met him, but a lot of the things that I've worked on over the years have found their way back to work that Ted did. So, and I'll try to introduce that during my presentation. So yeah, as I was saying, we're going to have to sort of navigate structural stability. For some of you may conjure up, oh God, a bunch of differential equations. This is going to be a nightmare. Not so. All right, I'm going to try to present it to you as in a straightforward way, and we'll go from there. I'd like to start by, again, focusing on the fundamentals and then moving on to your judgment and then doing a deeper dive on stability. So let's get started with the fundamentals. I know this E-room, if you will, is filled with brilliant engineers. I heard our numbers are up around 2,500. That's a lot of people out there. I wish I could see any of you, but and I know you're all brilliant, but I really would like to start here with some fundamentals because a lot of times when I get asked about stability questions, I find my way all the way back to they just missed one of the fundamentals along their education. And so that's where I'd like to go. So the first one is force follows stiffness in the wet spaghetti test. I'll go through these. The wet spaghetti part is more of a question, what if one of the members were to turn to wet spaghetti, a structure member that had no stiffness, what would happen to the stiffness of the system? So the first one that I'd like to look at is just a very simple 2-bar linkage here. And with respect to on the right there, I think you can see my cursor on the right, the relationship between the amount of force we put on the end of this member and the amount of deflection we get, that would reflect the stiffness of the system. Now, contributing to this stiffness are each one of the 3 connections and the longitudinal straightening of each one of the 2 members there. So in total, we could think of this really as 5 springs in series. So these members are in series, and if you wanted to compute the system stiffness, you'd have that sort of big gnarly equation down at the bottom. But really what I'm after here is the takeaway, and that is when you have a system of members in series, it's really a drag. It's not a good thing. The system stiffness is in fact smaller, indeed a lot smaller than the smallest of any one of the component stiffnesses. And so that's really problematic. Again, I'm not interested so much in your world of 2-bar linkages, but in thinking of a structural system, a lot of times you face situations where portions of the structural system have to be in series, and you've got to think about what's going on there and how poor the structure behaves when the stiffness is in series. One of the questions I get often is we have bracing, a whole bunch of bracing, it's all in series. And then the engineer will ask me, but we fixed the problem. And I said, oh, how'd you do that? We put another member in series, in that series, but it had a lot of stiffness. And honestly, they just made the problem worse. So it's just one of those cases where more material actually degrades the stiffness. The counter to that is when you have a whole bunch of members in parallel. That's a really good thing. One, it does provide you structural redundancy, so it's good from a strength standpoint. But from a stiffness standpoint, each one of those members, the total stiffness, each one of those members is contributing to the total stiffness. So it's a summation. So the stiffness of the entire system is actually a lot larger than the maximum of any one of the individual stiffnesses. So that's a really good thing. So try, if possible, and when you can, to get the stiffness of your structural components in parallel. The other thing to note is that the structure is alive and that the force distribution throughout the structure is going to follow the path with the largest amount of stiffness. And the reason this is important is sometimes I've got calls about a structural system and they had a moment frame, and the moment frame was fine. It was just a little too flexible. So at the last moment, sorry for the pun there, at the last second, they added a braced frame in parallel. Unfortunately, the braced frame is a truss, and trusses are remarkably more stiff than frames. And so most of the force started being attracted into the truss system, into the brace frame, and they were close to fracturing the connections in the brace frame. And they weren't really getting anything out of their original moment frame. So you do have to sort of remember that the load has many alternative paths, and the one it's going to follow is the one with the largest amount of stiffness. Next up on my fundamentals is sort of the basis of every structural analysis. And this side for me is always an important one. In structural engineering, as you're aware, we can really solve any problem we want, any analysis problem we want. We have more than enough equations. Our equations come to us in the form of equilibrium equations, and those are in terms of forces and moments. And then our equations also come to us in the form of compatibility equations. And those are less thought about, but equally important as the equilibrium, where equilibrium keeps forces and moments in agreement. Compatibility equations keeps the displacements and rotations in agreement. Now, we've got more than enough equations between the two. The problem is we don't have a common set of units. So in order to have all of the equilibrium equations, or all of ours be compatibility equations, all in terms of displacements or all in terms of forces, we need to move back and forth. And that moving back and forth is done through a constitutive equations. Constitutive, another more scary word, simply meaning something like Hooke's law some variation of it. The reason I wanted to emphasize this with respect to structural stability is a lot of times I'm asked, all right, how do programs or how do we actually account for geometric nonlinear behavior? How do we actually formulate equilibrium on the deformed shape or the undeformed shape? What are we doing? And all you're doing there is messing with how you formulate your equilibrium equations or your compatibility equations. So if you want to do a geometric nonlinear analysis, you formulate your equilibrium equations and your compatibility equations on the deformed shape. The second part of that is, all right, you got that down. How about material nonlinearity? I want to model yielding or concrete crushing or some combination. And the only way computer programs can do that is through the constitutive relationships, through the constitutive equations. So we have two forms of nonlinear behavior, one of them being accounted for through the equilibrium compatibility equations, the other through the constitutive relationships that you use. Just to show you where this all goes or can fit in, let's go all the way back to the oldest of the oldest stability analysis in the mid-1700s by Euler. I'm not going to go through the details here, but what I wanted to show you was what Euler basically did is the first thing is he formulated his equations of equilibrium on the deformed shape. So that's sort of the upper version here. Once he had his equation, his equilibrium defined, he made a substitution, and that substitution was the moment curvature relationship. That moment curvature relationship is our constitutive relationship. Once he did that, he had his differential equation, which he could solve. So he's played two of the cards. Now, the problem was his differential equation, the solution, had two unknown constants. So what did he do? He rolled up his sleeves and applied compatibility. And that basically said the deflections at the top and bottom, where those pin supports are, have to be laterally zero. And we could actually get to Euler's pi squared EI over L squared. And that still finds its way all the way into our specification in Chapter E, 0.877, and we're basically being multiplied by the Euler buckling stress. So now, that's 1750s. How about today? Today, it's awesome. We are running these amazing computer software packages. This came to me from my friends at Walter P. Moore. It's a SAP 2000 model of the Dallas Cowboys football stadium. Literally thousands and thousands, and maybe even tens of thousands, maybe even 100,000 degrees of freedom here. But if you were to sort of open up the SAP 2000 software, the first thing you would find in there is a whole bunch of computer code. And then you dig a little bit deeper and you'd find a whole ton of linear algebra. But keep digging, and what you are going to find are equilibrium equations and compatibility equations, and then you're going to find constitutive relationships that allow you to move between the two. So they're in there, and in fact, they're the basis for all of our analysis methods. Next up on my fundamentals is superposition. It's always so tempting to do this, just add up the effects, and it works fine as long as you have a linear response. Under serviceability conditions, everyday loads, yes, superposition is fine. On the other hand, when you start to talk about ultimate strength, when you talk about when a thing's going unstable, then the rules of superposition tend to break down. So you've got to ask yourself, all right, I'm applying superposition. Is it fair? Should I be? The last one is a little bit more focused on the behavior of steel structures, and I'd like to look at that from both a material level and a cross-section or strength level. So I'm going to try during this presentation to keep the atmosphere a little bit lighter, but this is kind of cool. But my lighter aspect is about 30 years ago, my family and I moved to central Pennsylvania, and we had to make a very critical decision when you live in central PA, and that was, are you a Philadelphia Eagles football fan or are you a Pittsburgh Steelers fan? And it was nights, and we spent a week wondering which way we should go. Just kidding. But in reality, we went with being Pittsburgh Steelers fans. For me, that was great as a Steel guy. There's the city of Steel in the background. But what I want to say, somewhat with tongue-in-cheek, is these Steelers fans are brilliant. Not only do they know football, but they also know steel. And so up at the upper left is a tensile coupon test that we've all seen, certainly as undergraduates. And you've always got your elastic range, followed by some perfectly plastic or some yielding, strained hardening, right through to rupture. I think one of the things that these Steelers fans know, but maybe you need a refresher on, is this diagram, as I'm showing it up here, is not at all to scale. When we put things in scale, what I'm going to do is take this point right here where everything kicks off, and let's call that the 0 yard line. If we get to yield on this football field, that is the 1 yard line. So we've only moved 1 yard. Then we come across the yield plateau, and we're at the 10 yard line. And then it's quite interesting. This all the way over here looks like the Hail Mary pass, literally is to the other end zone. So this is really, when you put things to scale, how much ductility steel has. It's amazing. It's a very, very ductile material, very high strength, excellent properties. The problem is just because you've got a material like steel that has all this ductility doesn't guarantee that any component you design with it will have the same amount of amazing ductility. And so I'd like to just kind of jump to this slide. Now, I could show you old historic photos of frac sheet connections, but today we've come a long way. And there's a reason why this graduate student is smiling. They've just conducted a test on a connection that you're seeing on the right there. And if you do things properly, if you follow the rules of AIC, you can get a lot of ductility in a connection. So a very well-proportioned steel connection can also represent that ductility that the material has. Over on the right is something I'm going to try to do throughout my lecture, and that is introduce people that have won the T.R. Higgins Award in the past, but have also contributed to the different areas of research. So that's who's on the left there. Those dates do not reflect their college graduation date, not at all. It's the year that they won the Higgins Award. And you can see quite a list of names, very famous people I'm sure many of you have heard of before. But the first one I want to start off with is Professor Popoff in 1972. The reason that's kind of key is he was the first recipient of the T.R. Higgins Award. And so now we go almost 50 years later, and this year's recipient for the 2020 award is Bo Doswell. So quite exciting list of folks, and many of them are friends of mine, so it's great to see their names. And a special shout out again to Bo for winning this year's award. So focusing on designing with steel, one of the things about steel is it has amazing strength to weight and amazing stiffness to weight ratios. Right? So it's very, very good material in that context. The problem is it's not free. It can be expensive, so you've got to come in with a competitive price. And by the time you combine those three, what you often end up with are very slender systems, very slender members, and in some cases slender cross sections. And when you have things that are slender, they want to buckle under compression. So as a steel designer, we basically have to design two things: connections, 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 and design for compression. The rest of it really is pretty straightforward. So we're going to focus not on connections, but on the buckling of the stability aspect. For me, this is a really important slide, especially when I was part of the group that sort of brought on the direct analysis method. And we sort of, in 2005 timeframe, realized that the profession had a fine education in buckling, but it primarily focused on bifurcation theory. And I'll use a couple examples to show you that, but no deflection and then a sudden deflection. The other possibility to that is what I'm terming as an instability theory to represent buckling, and that is you start with some small imperfection, some perturbation that grows. So let's start with a column. Over on the right is a column test that was being done years back at Lehigh. And my plot here on the horizontal axis will be the lateral displacement, and on the vertical axis will be the applied force, the compressive force. Just to get things a little straighter, what I've done here is I've taken that column, which was vertical, and just so I can fit it in my graphics, rotated it sideways. So we're squishing the column down we've got two possibilities. One, the column is perfectly straight. Load is concentrically applied. It's a perfect world, and nothing happens until we reach the Euler buckling load, and then it all breaks out and the column buckles, and we've got unbounded deflections. The more realistic possibility here is that the column is not perfectly straight. It has a small initial imperfection, or there is some eccentricity in the load or some combination of the two. What that does, at first, you start applying the load, and really not much. You get maybe a little lateral displacement, but then as we put more and more load on, what starts to happen is the bending starts to increase and dominate the problem, and we get a lot of bending followed by a lot of deflection, and if we're modeling yielding, we'll get a lot of yielding, and we can either simulate the elastic flexural buckling load of the column or the inelastic flexural buckling load. So again, two schools here. Let's check out a beam. It's the same concept with a beam. In the lower right here, I have a beam that's being subject to uniform bending. I've got the beam braced at each end, and I have a beam that, let's say at first, is perfectly straight, and everything's good. So what would happen is if I was monitoring the out-of-plane deflection for a bifurcation analysis, nothing would happen. No out-of-plane deflection, no out-of-plane deflection, no out-of-plane deflection, and then suddenly lateral torsional buckling would occur. On the other hand, if I were to actually include the reality of the problem, and there is a small initial imperfection, for most of the moment, not much would happen, and then suddenly we would get the gradual deflection out of plane, and it would grow into an instability, either elastic or inelastic. Now, when I say gradual, I don't mean in terms of time. I mean more in respect to being able to see what's going on. With respect to time, gradual is still very fast. These buckling phenomena occur very quickly. It's just that with this mode, you can actually measure it and detect it versus the other mode, it's either all and not at all. Two theories there. One more time, this is certainly the same situation with a structural system. So I've got a little story tube bay frame down at the bottom here. And in this case, all I'm doing is putting on the gravity load. And if I did a bifurcation analysis, it would nothing would happen to that frame, and then suddenly it would buckle. On the other hand, if I included an initial imperfection, or even interesting for this frame, because I put on gravity load on a non-symmetric frame, right from the beginning it starts to lean anyway, so I don't even need an initial imperfection. But what happens is, at first, not much, and then we start to get some deflections, some initial yielding, some bending, more yielding, loss in stiffness, larger deflections, more bending, and the response looks again like I was trying to indicate on those other systems. So two very different schools. The keys to doing the green and blue curves, the more instability theory curves as opposed to bifurcation, is that your stability analysis has got to account for the relevant deformations. You have to be formulating equilibrium on the deformed shape, and you need some type of perturbation, all right, usually in the form of a geometric imperfection. And you've got to be aware that there could be a loss in stiffness due to partial yielding, and that could be accentuated by the presence of residual stresses. It was this background that a group of us in early 2000 approached our opportunity to rewrite Chapter C in the forthcoming 2005 specification. At the same time, we had an excellent report by Bernstein and Iflin. It was an AISC report from 1980, and they had also identified a whole host of factors that influence frame stability. So we sort of knew the behavior I was showing you in the previous slides, and then we had this laundry list of what should be included. And what we did is we revised Chapter C, and we sort of included right at the beginning, before we talked about any stability analysis or design methods, this is what your stability analysis should account for. And it's basically what I was showing you in that previous slide. Any pertinent deformations, certainly axial deformations, bending deflections, shear deformations if they're significant, if you have significant connection deformations, you should account for them. Anything that would basically influence the deformed shape, because you need to consider equilibrium on the deformed shape. Consider the impact of initial geometric imperfections, consider the loss of stiffness, Due to partial yielding, with or without residual stresses, that partial yielding may occur. Of course, it's going to be more soon and more significant if residual stresses are existing in the members. And then these variations could occur just like any other variations that we account with phi and omega factors. So over the years, this has sort of become AISC's Chapter C Big Five. All right, so that was our review of the fundamentals. Hopefully you're good with that. Next up is judgment. And, I do some consulting, but I'm not a practicing engineer. I know there are thousands, it's hard to say, literally at least 2,000 practicing engineers of you listening right now. This is your bailiwick. You are all about judgment. And I just want to encourage you to continue to embrace every opportunity to exercise your judgment. Continually develop it, all right? You're not perfect now. You can continue to learn, and your judgment can be improved with every given day. Along with your judgment, you've got to consistently question it. What were the assumptions I made? Am I satisfying equilibrium and compatibility? So definitely take it on, but question it, continue to develop it. One thing I would really like to see, and this happens a lot at the really good firms, is conversations among colleagues about your designs. Some folks get so busy going on to the next project and the next project and the next project that they never have an opportunity, or they miss an opportunity to step back and just talk about the system that they just designed. What are the load paths, all right? You designed the building so it wouldn't fail, but just whispering back and forth, what if it did fail? How would it fail? What do you predict would be the ultimate strength of that structure? Plot the form, shapes, and moment diagrams. I am surprised how many times I'm called in as a consultant and the questions usually are focused around that the engineer has not plotted the deformed shape. The deformed shape of the structure can tell you a lot of information. And then, of course, there's the whole world of what-if scenarios. What if this connection were to fail or that member were to buckle? How would the forces redistribute? Do we have alternative load paths? All right. And judgment comes with years of experience. And so as new engineers, they need to be willing to be mentored, and the older engineers need to be willing to be mentors. And so there's a great relationship. And even the older engineers need to continue to be mentored and find people that they can talk to that have as many or more years of experience as they do. Just some stepping back and making our presentation a little bit lighter, I am convinced that someday soon, Nicholas Evans will produce a new book, no longer the horse whisperer, but the structure whisperer. And it will include our good friend, let's see, there we go. There we go. I get our good friend Bill Baker, who's the chief structural engineer for the Burj Khalifa Tower in the background. It's going to be exciting. And when that book finally gets converted to a movie, hopefully Robert Redford will star as Bill Baker. Oh, great days. And of course, I should mention Bill received the Higgins Award in 2013. Another good friend of mine is Ron Hamburger. Ron received the Higgins Award in 2006. He's a structural engineer with Simpson, Crumpets, and Hager. I should have mentioned Bill Baker with Simpson with SOM. But Ron does a lot of lecturing, and I had the pleasure of seeing him give the Kahn lecture down at Lehigh. And the talk was all about performance-based design, and is this the structural engineering profession's new hope? And Ron talked a lot about Robbie the robot replacing the engineer, and we should be concerned about this. Ron went on and talked about performance-based design as a great opportunity for designing structures like this temple. And it was just fascinating. But for me, the takeaway was, performance-based design, that sounds cool. But the real takeaway for me was once judgment is no longer required or needs to be exercised, then we have no need for the structural engineer. Then we can be replaced as a profession. So embrace that judgment. Don't let the computer dominate your mind. Right? You're the one running the ship here when it comes to your designs. Use your judgment, embrace it, and continue to fine-tune it. All right, let's talk a bit about designing for structural stability. This is one neat spot to just start. In the U.S., anyway, we have three different specifications. Upper left is for hot rolled steel. Lower left is for thin wall or cold form steel, and then lower right is not a steel specification, but an aluminum design specification. Now, I have the pleasure of serving on the specification committees for all three of these, and I just wanted to tell you something really cool that took place over the last few years. And when I was with the aluminum group, we went first, and we realized that the profession wanted to perhaps at times design out of aluminum, and it was a completely different format, different approach to aluminum design. And what we realized is that most people were educated based on the upper left manual there. So we completely changed the format of the aluminum specification to be consistent with AISC's. About a year or two later, AISI saw what aluminum had done and said, you know what, we're going to do the same thing. So the really good news for you folks out there now is we have one consistent format for three different specifications. And so what that means is Chapter C, Design for Stability, is Chapter C in all three of those specifications. Chapter E, compression members, is in all three of those specifications. Now, they might have different equations, but at least the format and the progress through the specification feels very similar. So that's a very, very good thing. Okay, so let's move to AIC's stability provision. So I came out and showed you AIC's Big Five. At the bottom of that, we come forward and boldly say, any rational method of design for stability is permitted. But the specification does go on a little bit further, and they provide two general approaches. And one is called the effective length method, K-factor approach, and that's been around since I told you earlier when Higgins introduced it in 1960. And then the newer kid on the block in newer 2005 timeframe, so that's now 15 years, and it's sort of become the staple of the profession, and that is this direct analysis method. So I'd like to talk to you about each one of them and just give you a feel for the opportunities that AIC has provided with these by including them in their specification. This is the money slide right here, and the important thing. For me anyway, in trying to explain when the direct analysis method first came out and listening to the profession and say, oh, that's what they're missing. Their whole thinking, their whole education was all based on the bifurcation theory, something suddenly buckling. And that lent itself perfectly to the effective length method. The direct analysis method, its whole concept lends itself more to this. You have a small perturbation that grows into an instability. And so once we could have that conversation, they realized that, okay, with the direct analysis method, I've got to stop thinking bifurcation, and I've got to more think, quote unquote, gradual failure. Gradual could be very quick and instantly or over a process of a few seconds, but gradual meaning it starts as a small imperfection that grows into a very large imperfection. Now, this is an important part here. Both of these methods, okay, and I'm just showing you the LRFD format here, the required strength being less than the design resistance. Both of these design methods require you to consider second-order effects, all right? When we came out with the direct analysis method, it seemed like the effective length people were saying, well, I'm not going to do that because I don't want to do a second-order analysis. As I indicated to you earlier with Higgins, he came out with moment amplification factors at the same time the specification came out with the effective length method. That was not by coincidence. They're linked, all right? So both methods require considering cap P delta, P cap delta, and P small delta effects. I showed this slide several years ago during an AIC night school, and it's kind of a fun one just to break up your attention here and just ask you, maybe it's time to add another bumper sticker to your car. And so a couple of things here, as I've had an opportunity to travel both domestically and internationally, a lot of international trips lately, I noticed, and the people often ask me, why do Americans put bumper stickers on their car? It's like a beautiful car. Why would you put all these gummy stickers on there? And I don't know, we sort of use them as opportunities to express ourselves. And so I also know that having grown up in New Hampshire, of course, they salt the roads up there. And so what would happen during the wintertime is we get a lot of rust, and then you've got to pull into a service station and get your car inspected, and you wouldn't pass inspection if you had too much rust. So by and large, what we would turn around and do is suddenly our car would have a lot of bumper stickers on it, and quite magically we would pass inspection. Anyway, so we do tend to use bumper stickers a lot in the U.S. So I showed this slide, and I said it might be time to add another bumper sticker to your car that says, reality is, think equilibrium on the deformed shape. Now, shortly thereafter, and for months to come, AIC had requested them for the bumper sticker. And the truth be told, there was no bumper sticker. I had just photoshopped this. Thing, and but I received a great surprise. I was at a workshop with Brent Liu from AIC in Honolulu, and when I showed the slide, Brent came forward and he had a handful, 50 bumper stickers that we gave the audience. And then from that point on, AIC's been kind enough to print up the bumper stickers. So had we been in person, I'd be handing you a bumper sticker. Unfortunately, on a webinar, I can't do that. But so look for your bumper sticker. Someday maybe we can meet, and I'll be more than glad to give you a bumper sticker. All right, let's get back to the show here. So including second order effects, I want you to know that there's two ways to do that. One is rigorously with the computer. All right, the loads are applied incrementally. There's a geometric stiffness matrix used. They update the geometry, but computer software, name your favorite package, can do a rigorous second order analysis. The second approach is to use B1 and B2 factors. That's an equally fine approach. It's just you really need to know what you're doing. So today, I would advise you not to go the B1, B2, LT, NT analysis and just push the second order analysis button on your computer. Yes, as an engineer, you're obligated to know how it got the solution, but let it do the work for you. B1 and B2 came out in 1986 with the first edition of LRFD, and the thing there is that there was no computer software available, commercially available, that could do the rigorous analysis. Those tides have significantly changed. Now, I do find that B1 and B2 factors are good to calculate. I don't like to use them to do my second order analysis, but I do find that they're important to calculate because they can provide me an indicator of if I'm having a stability issue with my structure. So that's where I'm sort of going here. So indicators of stability-sensitive structural systems. Certainly B1 and B2 factors are certainly there. I especially find the B2 factor decent to look at. Another possibility on these indicators is actually to just do a critical buckling load analysis. Most of your programs today are coming with an eigenvalue analysis. Let it go. And they're very fast, and they'll show you not only the buckling load factor, but the mode shape. Another fun one that we worked on was computing the natural period and comparing or assessing it with respect to its impact on second order effects. So years back, one of my previous students I just got to meet with when I was traveling for the Higgins lecture, Dale Statler out with Miss Jenny Elsner in Denver, him and I, and we had the pleasure of working with Les Robertson on this project, and we actually developed the equation in the upper left there that allows you to use the natural period as an indication of how significant your second order effects are. So it's very similar to a B2 factor, but it's based on the natural period of the structure. I think Eurocode does a real nice job here. Right in their specification, they sort of have a warning system that if you do an eigenvalue of a buckling analysis and you're getting your buckling load factor, that is the number of times against the applied loads that you have on there, probably the factored load combination. So you put the factored load combination on there, you ran your buckling load analysis, and if you get a buckling load factor less than 3, that you better wake up there, all right? You have a stability-sensitive structure, and you better be using a good, solid, rigorous second-order analysis. And this would equate to about a B2 factor of larger than 1.5. On the other hand, Eurocode says, look, if you're in the 3 to 10 range, yeah, it's all right. You can do approximate method or the rigorous, whatever, you'll be fine. And then if it's larger than 10, well, you know what, you don't really have a stability-sensitive structure. So we don't have this codified in the U.S., but it's certainly one of the first things I do when I look at a structure that's been designed. And, do we have a stability-sensitive problem here? I'll do a buckling analysis, eigenvalue analysis, and just look at that buckling load. And if it's coming in at 15, we don't have a problem. If it's coming in at 1.5, we have a serious problem. All right, so something to think about there. All right, so with that sort of background, let's have just a look at the effective length method for a moment. The thing about the effective length factor is that it's the one thing that's going to account for basically the big five. All right, so you've got one K factor for each member that's trying to account for all of those big five. You can certainly do that as long as you've got the correct K factor. All right, so just emphasis there. Make sure you know what you're doing when you use the effective length of the K factor approach. It's been successful since Higgins rolled it out 55 years ago. I was talking about Higgins rolling out this factor. I wanted to just let you know why he did it. And the primary reason was that the structures were becoming much more slender. They didn't have these huge infills anymore, masonry, exterior walls, or anything like that. They were becoming very light structures. That's what the architects of the time were doing in the late 50s. And so stability was sort of catching the profession's eye. And so, a whole range of group going all the way back to Jackson and Moreland had come up with systems or methods for calculating K factors, and the K factors found their way into the specification. It's funny to think Higgins at the time, the profession had to be convinced to use K factors. And no worries, just use these alignment charts, nomographs. They're going to do the trick for you. But just try and get Higgins back into my talk here. Can the K factor really account for all of those big five? Yes, it actually does, as long as you got the right K factors. But it does it indirectly, all right, through its conservatism. There are a lot of different methods for computing K factors. Probably the most popular is to go to those alignment charts that are in the AISC commentary. But you have to be very careful. Make sure you read the fine print. There's a whole host of assumptions that come with them. And as addictive and fun as they can be, there's a lot of assumptions, and most likely you're violating them. So you may have to modify how you actually use the alignment charts. On the other hand, you could do that eigenvalue analysis, and you could back calculate K factors. And several folks are doing that. The only danger is if you have a portion of a structure that's being controlled by the buckling, you'll get good K factors down there. But if you have another portion that is not controlled by the buckling, you're probably going to have some pretty light forces in those members. Light forces being in the denominator will result in big K factors. So things may spiral out of control there. So you've got to be careful. In 2000, Lou Geschwinder won the Higgins Award. In his Higgins Award paper, he provided a nice overview of both these methods. So the bottom line is how confident are you in your K factors? Now there are some great resources out there. So if you want to continue in your K factor person, more power to you. But if you want to do a deeper dive on proper ways to calculate effective length factors, I'd really encourage you to find this ASCE monograph that Jerry Hajar, who won the Higgins Award in 2007, put together. He led a team. He was the editor for a group, and it's a real nice piece. Another option is SSRC has a guide to stability design criteria. But either one of those two resources and in your knowledge about what the K factors are trying to do, and I think you'll be in good shape. But a good K factor gives you the right amount, a bad K factor, and who knows what you'll get. All right, let's switch then to the direct analysis method. We worked in a group, I would say probably starting in, I want to say 1999 through 2004 when we finally went forward with it. One of our chairs was Shankar Nair. Shankar won the award, the Higgins Award in 2007, where he actually presented on the direct analysis method. But the thing about the direct analysis method, the key, if you will, is the concept that the more things that you're willing to directly model in the analysis, the more simplifications you're going to be granted when it comes times to computing the design resistance. All right, so the more effort you put in the modeling side, the more simplifications you'll get on the design side of the design resistance terms. And I think that's really a key component. Now, there's always a time when you roll out a new method like we did that you have to name it. And the natural name for us was, it was a direct method. It had analysis, so we called it the direct analysis method. In hindsight, it did cause some confusion because people thought it was an analysis method, not necessarily a design method like the effective length method. It probably would have been better had we called it the direct modeling method. But that ship has sailed, and here we go. By directly modeling effects known to impact system, member, and cross-section stability, well, what are those effects? Well, those effects are basically back to our big five: pertinent deformations, the load distribution, the stiffness distribution, initial imperfections, the possibility for some yielding, and the impact that this will have on the stiffness of the structure. Those are the effects that you're trying to maybe one by one directly model. Let's put a little finer tooth comb on this and look at AIC's direct analysis method. Now, other specifications, as I indicated earlier, have their nuances as well. With AIC, most of our sections are compact, so we're not all the way down in the fines like maybe a thin wall specification would be in considering the direct analysis method with respect to cross sections. But certainly with respect to systems and members, AIC has some great options with respect to the direct analysis method. Like I said, in 2005, we came out with the direct analysis method. In 2010, it was upgraded from an appendix to the main body of the specification, and it continues there today. In the main body of the specification, the original direct analysis version 1.0 simply says, look, if you model the pertinent deformations, the loads and the stiffness of the structure, and you model the system imperfections, not the member imperfections, they'll be captured by the column curve, but the system imperfections, the outer plumb of the stories, and you account in some way for the possibility of yielding, and we agreed that a 0.8 on tau would do the trick. And then the simplification that you're granted is you can use the unbraced length and as the L sub C in computing the compressive strength of the member. So that was a huge advantage. You no longer had to calculate K factors, and you could get there. So that was well received, and you got a little work to do up front in the modeling. In 2016, we came out with another possibility, and that was, and that's in the appendix. So it's like a revision, if you will, to the direct analysis method. It's still elastic, but the engineer is going to do a very rigorous second-order analysis. They have to include the system imperfections, but they also go forward and include the member imperfections and a knockdown for the yielding. They've got everything there that the column curve was based on. So now, if a member instability or a system instability were to occur, the moments would get very large in the design, and you could check the design. So the simplification in adding that additional, you've got to model those initial member imperfections, is you no longer even had to know what the unbraced length was. You could just calculate the compressive strength based on the cross-section strength. And that was a big plus for some structures that I'll show you shortly. So in the end of the day, it's really all one big trade-off. I'm sort of showing you AIC's interaction equation. In the numerator are the demands, and in the denominator are the capacities. So these are the addition of the demand to capacity ratios for compression and bending here. If we look at the compression strength, what's shown in red, it seems like as we move from the effective length method with a K factor larger than 1 to the direct analysis method with K equals 1 to this more advanced direct analysis method where K is effectively 0, we're increasing the compressive strength of the column. And as much as that is true, P sub n is getting larger. What we are also at the same time increasing is the M sub u, the moment. The moments are getting larger in the direct analysis method because you had to model the geometric imperfection, the sway story displacements, and you had to have a knockdown 0.8 on top. If you go even one further and also model the member imperfections, the moments are going to even be larger. So it turns out to be one big trade-off. Yes, you're increasing the compressive strength, but at the same time, you're increasing the moment demands. And so at the end of the day, all three methods can give very similar designs. So just to sort of wake you up with this slide here, we're out here in central Pennsylvania, and we have a lot of cantilevered structures. And I'm always wondering, what did Mother Nature use? K equals 2 for the cantilevered cornstalk, 1 or 0? What? And my only point here, besides trying to wake you up with a graphic, is just to indicate that the building doesn't know how it was designed. It's just out there swaying in the breeze. You, as the structural engineer, you used your judgment. You used a method that you felt your confidence in, and you designed the building. So it's kind of fun. Some more thoughts here. We were never on ASC about trying to automate the process. It was always about trying to provide more opportunities for the engineer and more opportunities that replicated more realistic behavior. And so the real question is where, for every given situation, where is your confidence level? Is it high on the prescriptive specification equations, or do you want to relax that a little bit and move more into relying more on the analysis? So I'd just like to walk through a couple of examples. This is a pretty traditional orthogonal structure, steel structure. Here, I think any one of us could use the effective length method or the direct analysis method with great skill and use the specification quite well, and we'd get a fine design. So what's in the specification is great. It's fine. Sometimes, though, architects and structural engineers, we have this beautiful relationship with architects, but sometimes the architects come to us with columns that we don't quite understand. Sometimes they have structures with no columns. We don't get that. And then other times they come with columns that are these tree columns. So it gets a little bit tricky. You ask yourself, okay, let me calculate the K factor for this column. And you're looking at, all right, oh, wait a minute. That column is going in every direction. No K factor. All right, let me get the unbraced length. Oh, God. Is it the unbraced length of the trunk, one of the arms? All right, I don't know how to do that either. So this would be an example where the engineer might opt and come in and just model the member imperfections as well as the column or the tree imperfections and actually just design for the cross-section. All right, so that would be a case. Arches are another good example. This one came to me from my friend Larry Griffiths, who won the Higgins Award in '94. So yeah, we've got an arch, two-arch bridge here, a little pedestrian bridge. And the engineer at Walter P. Moore, the engineers were thinking, all right, what is bracing that arch? And are those verts really adequate in bracing the out-of-plane buckling of those arches? And so what they opted to do was model the member imperfections, that is the imperfection of the arch in between each one of the vertical struts. That's what I'm showing there as the member imperfection. And then the system imperfection was to take the entire arch and pretend it buckled out of plane. And so once they did that, they had modeled the system imperfection, they had modeled the member imperfection, they used a very rigorous analysis, they brought in a 0.8 on tar on the arch, and they were able to confirm the adequacy of the arch just based on its cross-section strength, knowing that the analysis would let the moments, or the analysis would indicate that the moments in the arch would get very large if it was reaching an instability. So good on them. It's a good choice. One more version of the direct analysis method appears in Appendix 1 under inelastic analysis. And here, you've got to go a little bit further and actually model the yielding and directly within the analysis. So you're actually doing an inelastic analysis. And the simplification you're granted is that you need to abide by the intent of the specification provisions, but not by the specification equations. And of course, you can also go beyond the first plastic hinge. So there's some real advantages to that. This was an example in Boston that my friend Rich Hennig from Lemessurier lent me. They needed to provide a big column-free atrium in this building here. It's a business school building, and they wanted this big column-free atrium. And the architect wanted no columns, but Lemessurier's company didn't want to go with a big bridge over the top. So what they decided to do was still use columns, but columns, and these are big, hefty columns, but they cut the webs out of the columns, and they created ladder columns. All right, so big, giant columns here, but they turn them sideways, and they practically go invisible. So they serve their purpose, but certainly well outside of the column curve presented in Chapter E of our specification. So the measuring company went all in with the inelastic analysis to design those ladder columns. All right, let's have a look at advanced analysis a bit, some background to it. I want to go back to Higgins' days in the late 50s. Actually, it even starts before that. It was in the 40s that John Baker at Cambridge University, a professor there, started to explore this whole concept of plastic design. And Lynn Beadle, who was at Lehigh University, went and visited Baker and came back to the U.S. with, oh, guys, you got to check out this plastic design. The concept was that you could actually go beyond initial yield. You could go beyond full yield of the member. You could keep loading until you got a plastic mechanism, and that's when the structure would become unstable. Of course, the profession was a little, what? Are you sure about that? So Lehigh would hold workshops and experimental tests in which they would bring in all of their people and the profession to their labs and actually run the tests. So it's kind of cool to see these tests, historical photograph here. Like I said, Higgins was convinced of this, and he led AIC to including Part 2 on plastic design to this 1960 specification. Now, it wasn't a time of webinars and the like, so Lehigh responded by having summer courses, and they also developed literature on the left, a book about it, and on the right, design guides, lecture notes and design guides, and it was quite successful. Some of the key players in that, Lynn Beadle won the Higgins Award in '73, Ted Galambos won the award in '81, and John Fisher, also at Lehigh, won the Higgins Award in '77. But it was a great group of engineers here, professors who put out these notes and really pushed the profession forward with plastic design. One of the first big buildings done in the U.S. was by Bill Bennett here in 1967. Bill used plastic design to design this 14-story apartment building. And it's right here in Binghamton, New York. It's a couple hours drive from me. So I actually drove up recently. I guess my side's a little old now, 2008, a couple years back. And I looked at the building and I was like, this is a landmark building. First one really done in plastic design in the U.S. And I felt like going up to one of the people and the occupants and saying, hey, did you know how famous your building is? But I was afraid they'd say, oh, no wonder the windows leak or something, you know. But anyway, it is kind of fun to see. Then it indicated a lot of advantages of using plastic design. It was a more rational method. There were some economies that could be gained. He actually could directly include second-order effects. But for him, it was important to be able to track the limit state behavior. What was the controlling failure mode? And then he could design accordingly or around it. The boat is now at full steam. AIC in '71, they released a nomograph on plastic design and steel. And they sort of predict the future, that once these computer programs arrive, we're going to be able to do amazing things with plastic design. And those computer programs, that hardware, the analysis software, all became a reality between 1970 and 1990. And I actually had an opportunity to be part of this in the mid-'80s as a graduate student up at Cornell. And this is just a shot from my PhD thesis in which what I did is I looked at frame after frame, and in this case, a 3D 22-story frame, a building. And what I was after was, if we design this according to just the current LRFD 1986 version, or if I go all in, so elastic analysis, LRFD, or if I go all in, LRFD inelastic, what will happen? And so I was able to design the frames using two different schools, and we're able to show the benefits of using inelastic analysis. It was to the point that my PhD advisor, Bill McGuire, who won the Higgins Award in '92, was able to chair an AIC Task Committee 117, and they started and sort of paralleled my research. I was reporting to them people like Radar Behovda, who won the Higgins Award in '87, Wi-Fi Chen at Purdue at that time won the award in '85, Gerhard Heyer at AIC, Jerry Iflin, Jay Larson, Stan Lindsay, down in the South there at Stan Lindsay Associates, Pack, and Joe Ura, who won the award in '74. Joe, of course, the professor at UT Austin. And this group also advised my PhD as well. So I'm still getting therapy for that, and they tell me I'll be normal in about another 20 years. So it's good. Now, it was fantastic to work with these, but boy, I really had to make every effort to bring my A game when I presented to such a distinguished set of engineers. There was one fly in the ointment, though, and our U.S. steel profession was very slow to adopt LRFD. So we really couldn't have design by advanced analysis unless the profession were going to move from ASD to LRFD. The rest of the free world, especially Australia, took the step immediately. They were only, they called it LSD, limit states design at the time, and so it was very easy for them to modify their specification and have an appendix on using advanced structural analysis. So good on them. We continued work here in the U.S. Don White, who won the Higgins Award in 2009, and Wai-Fai Chen led us, members of the SSRC, to prepare one book. Andrew Sorbeck edited and prepared a group of us to prepare another book. We were making progress, but the real break came in 2007, and that's when AISC formed a subcommittee that I had the pleasure of chairing, and we actually put forward and finally got approved in 2010 Appendix 1, designed by what I would call advanced inelastic analysis. It wasn't plastic design, it was direct analysis method, but based on inelastic analysis, and what I showed you earlier. It was great to work with people like Bill Baker, who won the Higgins Award in 2013, Greg Dierlein, Subhash Goel, who won it in 97, Rich Hennig, Dick Kaler, as I indicated, Bill McGuire, Chin-Min Wong at UC San Diego, won the award in 15, Don White, me, and Brent Liu. And then I was so pleased because we had finally done what Bill had set out as a chair in the early 90s, and we finally got this thing published in the specification. And Bill was in his early 90s. He was quite old at the time I got up there. I showed him what we had done, one big hug, and I asked him to sign it, and it was great. And then sadly, just a few months later, he would pass. But we got there. We finally got Bill what he had set out for. Now, inelastic analysis is really being pushed by seismic as well. They can see the advantages of having fuses and portions of their building yielding. And so that side has always been active. And today, when we're going to the extent of using full nonlinear analysis and time history analysis, and to the point that AISC right now has a task group led by John Hooper looking at two things really, the direct analysis method within seismic and a forthcoming appendix on how to use advanced nonlinear analysis, time history analysis in the seismic community. So good things coming on that front. Nate, I think I'm going to keep moving and not go to the video here, but one thing I want to just provide you an example is this Caltrans building. It was a structure that Jim Malley, who won the award in 2010, Jim's also the chair of the AIC specification. He lent me this example. He's an engineer with Degenkolb, and they were faced with retrofitting this building for higher seismic demands that had more recently been discovered. So they looked at a lot of options. One was just to increase the strength of the connections, and then they started toying with the concept of using or retrofitting the building with viscous dampers. And so over on the right is an architectural rendering of what these viscous dampers would look like. And I always try to get a chuckle and think of Jim Malley explaining to the office occupant, and the office occupant saying, well, wait a minute, if you put those big diagonals across my window, you're going to sort of block my beautiful view of the Oakland area. And Jim Malley, that clever structural engineer, says, oh, no, you have this all wrong. If I give you a viscous damper and a big 8.0 earthquake occurs, you're going to have a front row seat to this viscous damper pumping like crazy. It's going to be awesome. And then the office occupant says, oh, that's totally cool. And these Jim saying, in fact, I'll give you two, because they have to come in pairs. But anyway, but one of the things that they did is they actually ran lots and lots of time history analyses and nonlinear time history analysis. And maybe what we'll do is we could come back to the video later, but I'm running a bit behind in time. But what Jim was able to show, and Degenkolb engineers, is that the performance of the structure using full nonlinear time history analysis was much improved by using the dampers. And using the dampers, they only needed to retrofit a few of the connections. By the way, I understand some of that connection research was done by Chin-Ming Wong at UC San Diego, who I mentioned had also won the Higgins Award. But on the right, you can see without the dampers, they were going to have to retrofit a lot of the connections. So using very sophisticated nonlinear time history analysis, they were able to land in a good place and convince themselves and their owner that they should install viscous dampers. So again, using incredibly sophisticated time history analysis methods, and the computer model doesn't look too amazing or anything here, but it's very smart, and it provided them with the information that could inform their judgment. So as far as the direct analysis method, there's an excellent design guide out there that Larry Griffiths and Don White wrote. So those of you who are members of AISC or not, just go find that design guide, and it'll really get you moving in the right direction. The folks on the Higgins Award Committee also asked me to chat briefly about the paper that won the Higgins Award. So it's part lectureship, but it's also based on a paper. The paper was prepared, interesting enough, by myself and my wife, Constance. Constance is a professor and chair of mechanical engineering here at Bucknell. And when we're only primarily an undergraduate school, I get a graduate student about once every 7 or 8 years. And so we primarily work with the undergraduates, but when we really want to get into some detailed research, well, that's what we do in the evenings and on the weekends. So we're sort of our own postdocs. So on many projects, Constance and I work together, and it's a lot of fun. And it just so happens that this one won the Higgins Award. So I'll just tell you a little bit about what was going on here. What we were interested in was some of the clauses that appear in Appendix 6 on member bracing. And those clauses are primarily focusing on bracing individual members. And what we were thinking about was, what about systems? And specifically designing those braces for the stiffness in a system. Strength, I think the problem is good. You just add up the force effects. Stiffness is a slightly different beast, and that's what we approached. I'd like to mention that Joe Yura, I had already mentioned his name, but Todd Helwig and Don White, and Todd won the Higgins Award in 2017, but those three people have contributed a lot to the provisions that are in our Appendix 6. So Constance and I are trying to make one more contribution here. Now, to sort of appreciate what's going on, I need to just understand one fundamental concept of bracing. On the left column, the column is kind of freestanding there, and up at the top, I have the brace, and the brace has a stiffness, K subscript tie. It's like a tie. It's a bracing tie, all right? If that brace is not stiff enough, then what you can see in the center is we won't be able to use the steel effectively. The column will buckle before it reaches its full strength, and it will buckle just by lurching over. If we make the bracing just stiff enough, we don't need it super stiff, but just at the right amount, which we call the ideal brace stiffness, then as I'm showing on the right, then the column will achieve its full capacity. So we want to make efficient use of our materials, and to make the most efficient use of this column material, we want to make the bracing stiff enough so we can achieve the full strength of the column. And so that's what we call the ideal brace stiffness. Now in design, for a number of reasons, we usually use 2 or 3 times that, but even there, I'm going to show you some interesting results. The case that I'll just show you is 10 parallel columns. Good news is the columns are all parallel with respect to supporting, say, some gravity load. The bad news is the braces are all in series, and they're all to the right, adding up, so crossed, and they're in series, and they're anchored on the left side here. So that's sort of the drag about this. Now, if you just have one load on one of the columns, then the brace stiffness just needs to be the ideal brace stiffness. All right, well, that's fine. If you go to the other extreme and put the load on the furthest over column, there we go, then you've got 10 braces. They're all in series, so collectively they have 1/10 the stiffness, so you now need 10 times the ideal brace stiffness in order to buckle the furthest column over. Well, at this point, we've either had load on one column or the other. What happens if we put load on all the columns? And that was really where Constance and I focused on, and we found that it took about 45 times the ideal brace stiffness. And that was a pretty big jump. And my reading of the specification was, I hope we're not implying that we just need 10 times here. We need a lot more than that. And so where did the first 45 come up? I was just using trial and error and some computational analysis. But then Constance and I rolled up our sleeves, we ran the math, and amazingly, we were able to fit a very simple curve to what we were saying. And so that's what I'm sort of showing you here. That curve, N is the number of braces in series. And if you want to know how many times you need against the ideal brace stiffness, that's the A. And it's just 0.4 N squared plus 0.4 N plus 0.2. And my word, I couldn't believe it. In running eigenvalue analysis versus our approximation, 1, 2, 5, 10, 50, 100 columns, and our little equation was always within 1%. So that was neat, and that was one of our contributions. We went a little bit further and actually modified our formulation for an anchorage that might not be rigid, and the math down at the bottom sort of shows you where we got. And then we sort of ran sort of a gut check on, well, if the anchor is rigid, then we should return to the original equation that we had. If the ties are rigid, we should return to a summation P concept. And of course, looking back in the history, one of the first people to present on the summation P concept was Ted Higgins in 1965. Now, others had also looked at it, but I just found it interesting that Ted had also presented on this. In buildings, we could apply it. We got a whole bunch of leaning columns, all tied to the anchor, which in this case would be the portal frame. And we could use this math, but one of the things that happens most of the time is the tie stiffness is very, very large compared against the anchor. So we were sort of revert back to that summation P concept working for stiffness. On the other hand, the cold form folks are trying to develop gravity systems in which they put a whole bunch of columns in parallel, and they're trying to develop the full strength of all those columns in parallel. And so they have to look very closely at the stiffness of the struts running in between the columns. And that's what I'm sort of showing you here in the picture. And then you can see them going through about at the quarter points. That tie, the strut running through, has a lot of stiffness. The problem is the webs are quite flexible. And so, the strut, the weld, and the web are all in series at each point here. So you end up with a small amount of tie stiffness, and it could be problematic if the engineers don't design for it. And they're aware of it, and they're designing for it. Another place that's a lot of fun to play is with steel joists. And I had the pleasure even right up till this morning on working with the research committee with the Steel Joist Institute. And so here's a whole bunch of joists in parallel. Joists are very slender. And so I don't really, whenever I hear joists, I have to think system. It's a bunch of joists, but equally important in that system is the bridging running in between them. And so I had 8 joists in parallel. I didn't need 8 times bracing stiffness to buckle one of the joists. I actually needed 29. So the bump up factor is pretty large, but it is predictable with this little equation that Constance and I came up with. Always fun to have a steel joist story in here for you. This is on the left, just to show you how slender these joists can be. There's Ted Galambos, Higgins Award winner in 81. Actually, Ted's not very large and fairly light, but he's buckling a joist. So without the bridging in place, these joists, or the deck in place, these joists are very flexible out of plane. And you can see one of our research students in the center buckling a joist, and over on the right, one of our research students, just showing you how unstable it can be and the like. Now, kind of funny, that student there, he didn't weigh close to 300 pounds, so he got himself all kinds of steel weights and everything just to get himself up to 300 pounds. But it just sort of shows you how important the bridging is, or the deck is, to these joist systems. All right, so let's wrap it up. This is always a fun slide to show you Yeah, I'm convinced it's time to start teaching first graders structural stability. Here I am demonstrating with a student the buckling problem that the folks at Walter P. Moore had with their arch. And I don't know. I mean, I want to ask you, when was the last time you wore a crown to class? All right. So, and look at these smiles. All right. Now, of course, you're thinking all those smiles will evaporate in second grade when they have to learn differential equations. But well, we can wait till then. Yeah, at the university level, I think we need to continue to focus on teaching the behavior of metal structures. The profession does a great job at teaching how to design. We should introduce them to design, but most importantly, they need to leave our engineering students need to leave understanding behavior. The profession needs to continue to educate itself, and there's lots of online resources for learning all about stability. And so if I've got one myself that was mentioned earlier, the mastan2.com, free software, free guided laboratories on how to explore stability. You know, this is 1980s when I was a student at Cornell. We had our CAD lab with computer graphics doing full nonlinear time history analysis. It was an exciting time, and we didn't know any different. But here in the background is Professor Hajar, chair at Northeastern, and there he is as a student 100 years ago. But today's students, same concept. Now they've got their own laptops, but here we are doing stability behavior studies in my steel course. So it's exciting. All right, literally to finish up then at this point, I've been asked to talk about, well, what do you think the future of advanced analysis is and design? And I do have a couple of thoughts there. You can sort of see my crystal ball. The first one is, I think on the element side, modeling the member or modeling the connection, we've really exhausted that. I think we're pretty much there. I think the future is going to show a shift to modeling the demand side. Okay, earth, wind, and fire, not the rock group, but earth being seismic, like we saw. Time history analysis for seismic effects will most likely become the norm. Modeling for tsunami or avalanche. Wind, I mean, it could be so exciting to take the taps from a wind tunnel, the tap data from a wind tunnel on a structure and put it in as time-dependent forces in a structural model. That is definitely within our reach right now. And there really is no more nonlinear problem than fire. Fire breaks out in a component of a building. That component loses stiffness, and the second it loses stiffness, there's a massive redistribution of force. And Maria Garlick, a professor at Princeton, did a great job in her 2016 lecture, Higgins lecture, when she won the award, describing this. So a little shout out for her. One of the things that happened, and even when we were graduate students in the 80s, we would dream about the year 2020, when future speeds of computer would be so amazing, everyone would be doing a nonlinear time history analysis. And we really, really thought that would be the case. But the profession did something we didn't really anticipate. And that was, with the hardware and the speed, the profession moved from looking at 30 or 40 load cases in the 80s to doing much more of an exhaustive search and looking at 300 or 400 load cases today. And so, yeah, the designs might be better, or at least they've made absolutely sure they haven't missed anything. But it was a curveball we didn't expect. In the next 10 years, computers are going to get even faster. And so I'm hoping we won't move from 300 to 400 load cases to 3,000 to 4,000 load cases. I'm hoping the engineer will continue to add this number of 300 to 400, which is working well, but maybe isolate the 10 or 15 that are really controlling and do a deeper dive with a full nonlinear analysis to investigate how their structure would perform under these nonlinear effects. And then, of course, pushing this even farther is virtual reality, artificial intelligence, and the use of big data. All of this is going to have a big impact on our profession, but it has to be at how we use it. It's not there to replace us, all right? So anyway, I'm going to wrap up here and just explain where I tried to take you is from an emphasis on the fundamentals. We talked about intuition on behavior, the importance of education, how design guides and specifications work. I showed you a lot about computer analysis, but with the warning that don't let it control you. You're controlling it. Let it inform you, working with in the experience with you and your colleagues. And all of these things factor into your judgment. And they're not there to replace it. They're there to guide it. Nothing could be more true in the world of structural stability. This is the last time that I'll give this lecture. Like I said, Bo Doswell is next year's winner, so he'll be on tour. I just wanted to mention that AISC is kind enough with this award to be able to respond to people all over the U.S. and provide or pay for my expenses so I can go and lecture at different SEAs and SEIs and universities. And so this sort of concludes my T.R. Higgins lecture tour. Like the bumper stickers, I hope nobody starts looking for this T-shirt. Again, it's me in Photoshop. But it was just about a year ago. I started in St. Louis, and then 20 trips later, and literally I got in my last lecture on the 9th of March down with my friends down at Georgia Tech. And I think 2 days later, the whole world sort of stopped traveling. And I get to give it a webinar now. So I think that's sort of what I have to say. I thank you all very much for your attention, and I'll turn it back over to Nate for some questions. So Nate, are you on?
I'm here, Ron. Great job. Thank you very much for that. So I'm going to ask everybody to turn your attention to the moderator window. And we are going to move into the question portion of this presentation. And we start that off with a couple of poll questions for the audience. So again, this is now taking place in the moderator window as opposed to the presentation window. And there you should see the first polling question. So the question is as follows. Which of the following may impact the stability of a system and its components? Is it A, flexural, shear, axial, and connection deformations? B, second order effects, both P big delta and P little delta? Is it C, geometric imperfections? Is it D, stiffness reduction due to inelasticity? Or is it E, all of the above? So go ahead and give that question some thought, and you can participate by selecting the radio button next to the answer that you think is correct on your computer screen. Again, this question is, which of the following may impact the stability of a system and its components? All right, looks like the results are coming in, so I'm going to go ahead and close it. All right.
Oh,
Ron,
it
looks
great.
like almost everybody thinks it's E, and pretty much a negligible number of people picked the other options. Did they get it right?
Yeah, absolutely. So what I listed here were 4 of AISC's big 5 when it comes to stability. And they're the four factors, the 5th one being uncertainty, and that's sort of factored throughout our specification with P and omega factors and the like. But those are the key 4. Emphasis, again, may impact, all right? The engineer should consider these 4 things. There may be situations in which they use their judgment and they conclude that one of these things is not impacting the behavior. And so consider is also another key word. So thanks, Nate. Good job.
All right. All right. So let's see if the next question's any more challenging. This is a true-false statement. True or false? If 4 members in series define a system, then adding a 5th member of large stiffness to this series will increase the stiffness of the system. Is that a true or false statement? Again, the statement, if 4 members in series define a system, then adding a 5th member of large stiffness to this series will increase the stiffness of the system. Is that true or false? All right, let's go ahead and go to the results. All right, Ron, looks like slightly more disagreement here, but about 90% of folks out there think that answer is false. What do you think about that one?
It is definitely false. As I was trying to illustrate, these members are all in series, so regardless of how stiff that additional member is, it's going to have some amount of stretchiness, and its stretchiness, if you will, is going to degrade the total stiffness of the system. So false on that one. Those that were true were probably thinking more of things in parallel. But when things are in series, it's just not a good day. If you can work to, sometimes you can avoid it, and you just got to understand what's going on. But other times, if you can provide an alternative in which the members are, or the components are in parallel, that's going to be much to your advantage.
All right. Well, good job, everyone. Those questions. So we'll go ahead and get to some questions that have rolled in from the audience during the presentation, Ron. I'm going to start by going back to slide 15. And again, we're just staying in the moderator window to see that slide. And so the question is, can you also add, say, Ka and Kb, et cetera, representing stiffness of the connections to this analysis? Do the bolts count or control these types of studies that you did, and did you ever add connection stiffness into some of these studies?
That's a good one. So let's take it one piece at a time. So let's consider number one all the way on the left, and I call that K red. That's the stiffness of everything there. It would include three pieces that are in series, the two connections and the strut in the middle. So once I sort of determine the stiffness of that individual piece, which would include the two connections and the strut, then I would have K red, and I would have done this for each one of the three bars, and then those are the things that are in parallel. So what the person's getting at, I think, is that in reality, what I have is three parallel systems, and in each system, I have a series. All right. And so, but the point is that things do get much better in parallel. As far as the more difficult question, and it's just so case dependent, is how much does the connection impact the stiffness of the member or the system? It just varies from problem to problem. I think my rule of thumb would be if it's a rigid connection, a moment resisting connection, a full restraint connection, and it's been designed that way, then I'm going to model it as a rigid connection in my analysis. If it's on the other extreme, the moments aren't necessarily being designed for, just the axial forces of the shear, then I'm going to model it as a pin. And then if the engineer is aware and purposely designing the connection as semi-rigid, and the person, maybe the engineer or an alternative company is designing the connection to be partially restrained, then I am going to absolutely make sure I include the stiffness of that partially restrained connection in my computer model. I may include it and find out it has no effect, or I may conclude that it's just one connection in a building that has a lot of different alternative load paths, so it probably won't have an impact. But I definitely would pause and give it some thought. So good question, hard one.
All right, let's back up a couple of slides. I'm now showing slide 13. This question was, we actually had a few questions coming in around this idea of stiffness in series. And folks are wondering what the implications are for frames. And so the question here is, regarding stiffnesses in series, am I to understand that if we start with a frame with stiffness K1 and then add another frame in the same plane as that with stiffness K2, would that actually be a smaller stiffness than the smaller of those two frames? Is that analogous to what you're talking about here?
All right. Great question, and I'm glad I got the opportunity to clarify this. So what we're going to do there is we're going to have two frames that are side by side, and those frames look like they're in series, but in reality, they're in parallel. and they're acting in parallel to resist the lateral load. So even though the two frames are side by side and it feels like they're in series, the problem for that one is actually the next slide, in which the two frames are acting in parallel. They're acting together. Each one is taking on some of the load, some of the lateral load to resist the force. So that example that the person laid out, I see where the confusion is. They're side by side. They feel like they're in series, but in reality, they're in parallel. Each one is intending to do some work in resisting the lateral system. Now, if the struts in between the two frames are not adequate, are very, very soft, no load may be getting into the other frame. But in general, if you have two frames side by side, each one should be doing their share based on their own stiffness in resisting the load. But yeah, good question.
All right. Going to slide 47, some interest from a few folks about sort of the aligning philosophies of these separate specifications. The question is, with these three material standards becoming more consistent, how are their respective cycles being handled? Is AISC coming first and the other two are following, or is there some other arrangement?
That's a good question. I don't think I haven't seen any on any one of the three specifications saying let's take ASI or aluminum saying, wait, steel's coming out with theirs in 2022. We should come out with ours in 2023, just in case steel makes any changes. Now, each one of these governing bodies for the specifications are creating their own rules, and they're updating their specifications similar to AISC on 6-year cycles. But in fairness to them, the format, where what is and where it is similar, but the actual development of the codes are three separate entities that are going along. Now, I am asked often at ASI and aluminum to, hey, what's the latest at AISC, and give them some, we're considering changing this. You guys might want to consider that as well. But the revision dates are not necessarily being guided by AISC. I find that they're more guided by having a look at when ASCE7 or IBC are changing, and they're trying to be more in tune with that schedule than necessarily AISCs.
All right. Going to slide 62, we had some questions about the general direct analysis method. And a few folks are just trying to understand what types of systems can they apply these to. And a few that were thrown out there are, what about truss frames or cantilever column systems? Another person is wondering, can this be applied to seismic applications? So you have any thoughts on that?
Yeah, a great question. Let's take it in parts. So the first one is on a truss. Well, again, it varies from truss to truss, but if I have a very slender, very tall truss, then my tendency would be heading towards the direct analysis method. If I have more of a normal truss that might be used as a lateral system in a building, in a 5-story building or something, then it's sort of interesting because in general, with all these pin connections, you'd be thinking of K factors of equal to 1, and the effective length factor would tell me K is equal to 1. The direct analysis method is telling me K equals 1, so 1, and I just use K equals 1, and whichever method is the easiest. And so I think, so I may have just made a case there for going with the effective length method, but I think what I'm really saying is the direct analysis method should be defaulting to the effective length method in a truss. You say, well, what about that 0.8 on E? The direct analysis method says I need to have it there. Yeah, go ahead and put the 0.8 in your truss analysis, or don't. You'll get the same force distribution. It's not going to have a big impact because the truss is so stiff. It's very rare that we have our second-order effects. When we will get second-order effects in a truss is if it's a tall, slender truss. Then we've got to scratch our head. I know the third one had to do with seismic. The seismic world, that's really what John Hooper's TG that I have the pleasure of serving on the AIC. John's guiding, a group of us are guiding some research that Larry Faunestock, Professor Faunestock at University of Illinois Urbana-Champaign is doing, research funded by AIC, to see if they can make some progress into better dovetailing the direct analysis method with the seismic design. And so, simple questions like, well, look, Don, you said the direct analysis method needs to consider geometric imperfections. What happens on the seismic side? Do we need to include them? It seems like once an earthquake happens, those initial imperfections are going to be like dust compared to the rest of the damage that's being done. And they're right. But best to do some research before we dismiss that. Likewise with the TAW factor. The 0.8 factor may be a little bit more of a chin scratcher there. But there's research going on right now, sponsored by ISC at Illinois, to sort of address the seismic question. Nate, I couldn't remember the middle one.
Yeah, that's all right, Ron. We'll add that to some of the questions we weren't able to get to since we are running out of time here. So thank you, everyone, for those questions. And I guess just want to let you know we did receive all the questions that you submitted, and we'll see what we can do here at AISC about following up with those question askers about some of their questions. Thank you to Dr. Zemian for presenting today, and thank you all for joining us. For everyone at AISC, I wish you well and look forward to seeing you soon. Take care, everyone.